Hello, dear fellow scholars. This is a new episode with a special guest. Today we are going to do something very cool. We will dive deep into PIC controllers, how to tune them, and how to use them properly. By the end of this episode, you will be able to understand how to use them and, more importantly, how to tune them so you can use them in practice. And I am sure you will agree with me that looking at their simplicity, they are really hard to tune in practice. So this is a hugely important skill. And I cannot wait to share my learnings with you. Before we start, yes, I'm doing these videos every week, and no, it doesn't get any less work than it did in the beginning. But I hear from you all the time that you love it, so I hope you find it useful. If you don't mind, let's keep this train rolling. So what is a PIC controller? PIC stands for Proportional, Integral, Derivative. It is a control loop feedback mechanism used in industrial control systems, robotics, and even IoT devices and autonomous machines. They are used everywhere. Their job is to achieve stability, accuracy, and smooth response. Now, why do we need such a thing? Well, imagine you have an autonomous vehicle and you press the accelerator pedal. You don't need to continuously correct the amount of pressure you put on the pedal, but you expect the car to reach the desired speed smoothly and remain there. That is exactly what a PIC controller does. Its job is to minimize the error between a desired set point and the measured process variable by adjusting a control input. Here, the set point is the desired speed and the measured process variable is the current speed of the car. The control input would be, for example, how much gas to give to the engine. We typically denote the controlled variable with a lowercase y and the set point with a capital R. The difference between the two is the error, which we denote with E. As you see, the goal of the PIC controller is to drive this error to zero. A PIC controller computes a control signal based on three separate terms: the P term, I term, and D term. The P term or proportional term is proportional to the current error. In other words, if the error is large, then the P term is also large. The I term or integral term is proportional to the integral of the error over time. And the D term or differential term is proportional to the derivative of the error over time. You might have noticed that in many control applications, the goal is to go somewhere and stay there. So if we look at the proportional term, it will drive the system to that set point, but not necessarily stay there. To achieve that, we need the integral term. The idea behind the I term is that it drives the system to the set point and stays there. Why? Because the I term is proportional to the integral of the error over time. This means that if the error is not zero, then the integral of the error will be positive or negative depending on the sign of the error. This means that the I term will be non-zero. The larger the error, the larger the I term. The goal of the I term is to cancel out the error so that the integral of the error over time becomes zero. When this happens, the I term becomes zero and the system remains at the set point. The third term is the D term, which stands for derivative, and its role is to predict what is about to happen to the error and prevent it from happening. For example, if the error is increasing, then the D term will try to decrease it. This can be useful, for example, when the system is close to the set point, because it can help to prevent overshooting the set point. Now here comes the fun part, and that is putting it all together into one single equation. It looks like this. You don't need to understand each and every step of this derivation, but I'm happy to walk you through it in the comments. But note that the result is worth writing down because it allows us to simulate it on a computer. This is the discrete version of it. That is, we only have measurements at discrete points in time. As you can see, the output of the PIC controller depends on the current error, the integral of the past errors, and the derivative of the error. And that is everything that you need to know about the PIC controller. And this is the most common form of it. Of course, there are more advanced ones as well, but trust me, by the end of this video, you will be able to write your own PIC controller from scratch. But now the question is, how do we tune it? Well, it turns out that there is quite some theory around this, and the way I learned it was through trial and error. Luckily, I found some really good recipes that I would like to share with you. If you have already worked with PIC controllers before, please let me know in the comments how you tune yours. And I am curious if there are other techniques that you would recommend. So the first technique is manual tuning, and it works like this. If you don't know anything about the system beforehand, Then you can just start by setting the integral and derivative terms to 0, and only use the proportional term. And you can increase the gain of the proportional term until you get steady oscillation. Once you have done this, you can then add the derivative term and increase its gain until the overshoot is eliminated. Then you can add the integral term and increase its gain until the steady state error is eliminated. This is not the most rigorous way to tune the PID, but it is a simple one and often leads to a good starting point. The second method is called the Ziegler-Nichols method, and it is probably the most widely used method for tuning PID controllers. It's a really good starting point and usually gets you pretty close to the optimal values, and it consists of 3 steps. First, as with the manual tuning, we set the integral and derivative terms to 0 and then increase the gain of the proportional term until the system oscillates. At this point, the gain of the proportional term is called the critical gain, which we denote with Q. Next, we measure the period of these oscillations and call it 2. Finally, we can calculate the gains for the pi and PID controllers, and I have summarized them in this table. So once you have the results from the previous step, you can just plug them in and you get the optimal values for the pi and PID controllers. And finally, we have the software optimization approach. And this is my favorite one because it is the easiest to implement and often leads to the best results. Here we use some sort of optimization algorithm to find the best values for the gains. This can be done, for example, with Bayesian search or genetic algorithms. There exist entire libraries for this task such as Skeeto Optimize. However, for smaller problems, you can also do it with a software like Python's built-in Optimize module. And then after some fitting, you get the optimal values for the gains. Let's look at a Python simulation of the PID controller. And for this, we will use the code provided by Jake Vanderplas. Thanks, Jake. And this is what we get. I hope you agree with me that it is so neat that such a simple algorithm can yield such great results. However, there's one caveat to using PID controllers, and that is that they are not silver bullets. They are easy to understand and implement, but they are difficult to tune. And the problem is that if you tune them incorrectly, they can cause instability or poor performance. The art of tuning PID controllers comes from experience and trial and error. And the best way to learn how to tune them is by experimenting with different values and seeing what works best. In the next episode, I will show you how to use the PID controller in Python and Arduino and how to control a DC motor with it. And if you don't want to miss that, then subscribe so you don't miss it. And yes, you heard right, subscribe. I am building a fully automatic PID-controlled robotic arm with a custom neural network, camera, gripper, and cloud connection. And I am making weekly progress videos about it. Don't miss them. Thanks for watching and for your generous support, and I'll see you next time.